So hi everybody, I'm Jaafar. I'm from École Polytechnique in Paris, and I'll be trying to talk about my work in T2K Experiment, which is regarding the Near Detector Upgrade and the sensitivities to constrain nuclear effects with this upgrade. So I have a lot of things to discuss, but I will try to just give you a taste of some of the things we do at T2K. So we heard a lot about neutrino oscillations and the mixing matrix, but I just want to focus on what long baseline experiments try to measure. So with the disappearance probability, we're sensitive to the theta 2-3 and delta m squared 3-2 parameters with the disappearance probability. And with the appearance probability, what we see is the sensitivity to this delta CP parameter, which depends on whether we consider neutrinos and antineutrinos. And we heard about the fact that we can reach CP violation if we measure a difference between these probabilities, which could explain, which could shed light on the matter-antimatter asymmetry that we have in the universe. And T2K has reported some first hints of this CP violation by excluding at the 2 sigma level the CP conservation hypothesis, which made the cover of Nature a couple of years ago. And yeah, just a few words on the T2K experiment. So we have an accelerator at the east coast of Japan here. So with the proton beam of 30 GeV, we produce muon neutrinos that first are measured. So the muon neutrino flux has this shape and it's centered around 600 MeV. And it is first measured at a set of near detectors. So the near detectors measure the unoscillated flux, which allows us to measure neutrino nucleus interactions and the composition of the flux, just to understand what it's made of. And the goal is to reduce systematic uncertainties. So there's an upgrade of this near detector, which I'm going to be discussing in a few moments. So the beam propagates for 300 kilometers to reach Super Kamiokande, and you can see here the composition of the flux, which has a maximum disappearance of muon neutrinos, and we have appearance of electron neutrinos. So the experiment was tuned to have this 600 MeV energy to have a maximum disappearance. And at Super Kamiokande, we can measure the electron neutrinos or muon neutrinos thanks to their ring pattern, and also measure the neutrino energy. So what we do in T2K is then measure the event rates as a function of the neutrino energy at the near detector and at the far detector. And if everything was perfect, what we would do is just take the ratio of that and then obtain the probability of oscillation. But actually, like, there are big differences between the near detector and the far detector. So we have to use models that can account for these differences. So these differences are like the fact that we have different fluxes due to oscillations and due to just the geometry. The fact also that we have, so at the far detector, it's made of water, so interactions occur on oxygen, whereas at the near detector, it's made mostly of scintillator plastic, so it occurs on carbon. So we need to account for these differences with models. And what we do is just perform a near detector fit that uses the data from the near detector to constrain the flux and the neutrino interaction model. And we use these constrained models at the far detector with Super Kamiokande data to obtain the oscillation parameters. I just want to stress here about the importance of reconstruction of the neutrino energy, since the probability of oscillation depends on it. So if we want to have a good reconstruction of the neutrino energy, we need a good reconstruction of the particles that come out of the neutrino interaction, and also a good model that can give us the neutrino energy. And here you have just an event display where the neutrino comes from here and hits a particle from our near detector, and we reconstruct the particles from this interaction. So if we want to improve this, we need to improve the detector and improve the nuclear model, which brings me to this first element, improving the detector, which is the goal of the upgrade. So the upgrade so the current detector has been good to perform all the data analysis that we obtained until now, and it has some limitations. The main limitations is the fact that it is non-isotropic. It is mostly efficient at reconstructing muons that are forward with respect to the beam, whereas Super Kamiokande, the far detector, is more isotropic. So we have a mismatch between the phase spaces between the near detector and the far detector, which increases our systematic uncertainties. And it also cannot measure the nucleon that comes from a neutrino interaction. It does, but it's a very low efficiency and a high threshold with respect to the true spectrum that we expect. So because of this, the measurements of oscillation parameters only uses muon kinematics, because that's what we measure best at T2K. So the goal of the upgrade is to overcome these difficulties and limitations. And the main part of this will be the installation of what we call the super FGD, super fine grain detector. It is made of 2 million cubes of 1 centimeter, and each cube is read through 3 directions with optical fibers. So when a charged particle crosses the detector, we have light deposition in the cubes, and this is read with the optical fibers. And with this, we would have a more isotropic response to charged particles. And the granularity of this super FGD will allow us to have a low momentum proton threshold for measurements. And we can even do neutron detection with this detection. So we saw how we wanted to improve the detectors. Now improving the neutrino interaction model. So we heard from Rakim this morning in the lecture about the different interactions that can occur. And here you have, as a function of the neutrino energy, the different cross section from the different interactions, and you also have the flux. So you see here that in T2K the flux is at 600 MeV, and the dominant interaction here is the CCQE interaction, where we have the neutrino interaction with the nucleon. So if we want to estimate the neutrino energy, we need a good model that's going to allow us to go back to neutrino energy from the outgoing particles. And so this is the focus of this talk. And I'm just going to focus on one element that we need to model well for this. And this is the fact that the neutrino interacts with a nucleon that is bound within a nucleus. So either carbon or oxygen, for example, in the case of water at Super Kamiokande. And the fact that it is bound, it has some premium motion. It has a non-static initial state. So one way to model this, which we started to use, the T2K, is the special function model. This gives us the distribution of energy and momenta of the nucleons within the nucleus. And we can see here for the case of carbon, we have the P shell and the S shell. And this is built from electron scattering data. And we can also account the contribution from strong range relations. So these are interactions of the neutrino on strongly correlated pairs of nucleons, and it gives us 2 outgoing nucleons from this interaction. And as I said, we started using this in T2K since 2020, and we have some uncertainties on different elements of these models. The first uncertainties are just the distribution of the energy. So we saw that we have different shells, the P shell and the S shell. It's just how much contribution comes from either shells. We also have uncertainty on the shape of the distribution of the momenta within each shell, and also an uncertainty on the contribution from these short-range correlation effects. So here I just want to compare with different models, so that are based on Fermi gas assumptions, and we see that the special function model is what's able to capture this rich shell structure of the nucleus. And I just want to finish with some projected constraints on these uncertainties with the upgraded detector. So as I said, we expect to reconstruct nucleons better with this upgrade. So we can use this information. And here I'm just showing this plot where we have the relative uncertainty as a function of data taken. So here you have to what year this corresponds to. And we are considering, so here the uncertainties, so I said on the occupancies of the P shell and the S shell for carbon, the contribution from SRC, and the shape of the distribution of the momentum of initial state nucleons. And we're considering 3 scenarios. The first scenario is when we have no upgrade and we use only muon kinematics. The second scenario is when we install the upgrade and still use only muon kinematics to perform our fits. And the third scenario is using the full power of the upgrade, which includes also nucleon information. And we can just see that the use of nucleon information, because we put more information in our fits, then we expect to have better constraints. So I'm not going to go into the details of this, but yeah, we can go up to a factor of 2 in improving the constraint on some of the uncertainties. Okay, so just to summarize, I said that T2K is currently working on the upgrade of its ND detector to reduce the systematic uncertainties and increase the sensitivity to the CP violating phase. And the goal is to be as sensitive as possible to CP violation before the start of hyper Kamiokande. We will expect to have an improved reconstruction of the low momentum protons and even do neutron detection with the upgrade. And we started estimating the impact on the constraints of the neutrino interaction model. And the next step for us is to check the impact on the sensitivity to the oscillation parameters with these improved constraints. That's all I want to say.
Thank you, Jaafar. Are there questions?
Yeah.
So you should probably know this already, but what's the timeline for Super FGD again?
What's
the timeline?
Oh, so we are hoping for it to be installed by the middle of next year.
Okay.
So yeah.
Okay. And it's meant to keep running when we switch to Hyper-K, right?
Yeah.
Okay.
Any other questions?
I'm sorry if this is something I'm supposed to know already, but it seems like a lot of these cross-section uncertainties are affecting our measurements because the near detector and far detector use very different technologies. Why do they do that? Why aren't they just using the same basic detector setup?
So yeah, that's a good question. I mean, so we used Super Kamikande because it was there, so that's something we can already use. And for the need detector, so I think it's just a matter of the space that's available to have the detector. So it is made of just plastic. It's true. We have some layers of water at one of the detectors here that allow us to have some similarity with the far detector. But it's true that it is different. And yeah, my guess is just because of some constraints on the cost and the available space.
So there's not like a separate physics goal that you can meet by using this plastic.
So we do cross-section measurements with this different detector, but ideally we would have wanted to have the same thing for both. I would say. Okay. If, yeah, maybe Andres knows more about it.
So I guess as compared to Nova that has essentially the same technology in both detectors, the problem with having the same technology in both detectors is that sure, you don't have to worry about certain systematics, but it also means that you don't know how to quantify them, which can be problematic if you have more neutrino programs. And also, I mean, these technologies are not scalable, right? So sure, ideally we would have a super FDG the size of Hyper-K in the Hyper-K side, right?
Yeah.
And water Cherenkov is not great for a near detector. So, and yeah, Hyper-K is just so big, right? Which is great. It's going to be great. So yeah. No. There are benefits essentially.
So the spectrum that you did show about the neutrino interaction, so are you talking mostly about the on-axis spectrum or the off-axis?
So so you mean the off-axis beam from T2K?
Yeah, like in the Super Kamikande, you have 2.5 degree off-axis.
Yeah, this is the off-axis, what I was talking about, yeah.
Okay.
So the on-axis spectrum is a bit larger and is more at 1 GeV. The off-axis spectrum is at 600 MeV.
Oh, thank you so much.
Sure.
Okay, let's thank Jaafar again.